The next thing we want to consider is the arc length as a function. So we'll define the function s of x as the integral from a to x of the square root of 1 plus f prime of t squared. Where here, this is essentially an arc length integral where we're treating the right endpoint as a variable. So here we imagine it's finding the length of a curve that starts at some point A, and the right endpoint is treated as our variable x. So depending on x, we could have this arc length would compute different values of the length. So we imagine this function f of t could continue, and so then I could input different values of x, for instance here, and it would give me now a new arc length from A all the way to x. And one thing we want to notice is that if we've defined s of x equal to this integral, then the derivative of s with respect to x using the fundamental theorem of calculus will be equal to the square root of 1 plus f prime of x squared. Which as a function, right, this is now just the integrand of our arc length function, where the input value again was this endpoint x. And if I use if I write the differential of this, so ds, which is just ds dx times dx, the differential dx, this will be 1 plus square root of 1 plus f prime of x squared dx. We can also think of this as the square root of 1 plus dy over dx squared. So thinking of it this way, we can also write this with this other notation. And something to point out is that if I have the arc length of a function that's x equals a function of y, this could also be the same as square root of 1 plus dx over dy squared dy. So notice that the difference here is that here we're given some function y equals f of x, and we're taking f prime here and then squaring it, versus here we're given x is a function of y, some function g of y. And so this would be our g prime of y here squared. So it gives us a consistent way to represent either of these two forms. And in addition, we could also have a slightly different version of this that looks more like the Pythagorean theorem. And in this case, it's sort of representing another way to look at it. So with these different representations using this differential ds, notice that here now we can express the arc length formula as the integral of ds. Let's just demonstrate this arc length formula. Suppose we want to find the arc length function for the curve y equals x squared minus 1 over 8 ln x, taking the point 1, 1 as our starting point. So here I'll write it as the integral from 1 to x, square root of 1 plus f prime of t squared goes here. What is f prime? Well, let's write it out. It'll be 2x minus 1 over 8 times 1 over x. So I'll write minus 1 over 8x. So let's insert that here. Give myself a little more room. Oh, and I should also keep in mind that here we're integrating with respect to t because x is the variable that we're putting in the limit of integration. And now we'll integrate. So in this case, to integrate here, I got to do a little bit of a simplification with this square root. What happens when I FOIL this out? So I'm going to have 2t squared, which is 4t squared, and then 2t times negative 1 over 8 times 2, so that'll be minus 1/2 for the middle term, and then plus 1 over 64t squared, and then when I combine 1 minus 1/2, notice that it makes this middle term change from a minus 1/2 to a plus 1/2. And what I notice is now it's the same thing that we had before. In other words, if I compare this expression here with this expression here, it's almost the same, but now it's changed that minus 1/2 to a plus 1/2. So I can use the factors that we had here when I FOILed this guy out, right? It came from this expression, this perfect square expression, 2t minus 1 over 8t, quantity squared. And since here we have the same expression but with a plus in the middle, we know it's going to factor back into something very similar but with a plus in the middle instead. So we know that this is going to factor into a perfect square factor, where I have 2t plus 1 over 8t. And then the square root now simplifies, and I'm just left with 2t plus 1 over 8t, which now is a very simple integral. It'll be t squared plus 1 over 8 ln of t, going from 1 to x. And now when I evaluate, we'll have x squared plus 1 over 8 ln of x minus 1 squared plus 1 squared plus 1 over 8 ln of 1. Of course, ln of 1 is 0, so we're just left with 1. Okay, so it'll be x squared plus 1 over 8 ln of x minus 1. So what this now gives me is the arc length of the curve 1 over x squared minus 1 over 8 ln x from 1 to x.